Okay, we are finishing up Module 3 with lessons 13 and 14 on the topic of the Pythagorean Theorem. And lesson 13 will be a proof of the Pythagorean Theorem, and for your problem set you'll get some more practice using the Pythagorean Theorem. In lesson 14 we'll look at the converse of the Pythagorean Theorem. So you should have already done the end of module assessment. None of this material will be on the module 3 assessment. So you can finish that up and then work on these lessons. Okay, so let's get started. So if you remember from module 2, when we talked about the Pythagorean theorem the first time, it's based on right triangles. So we need one right angle, which we have here at vertex C, and these right triangles have a certain amount of vocabulary. The side directly across from the right angle is called the hypotenuse, and the other sides of the triangle next to or adjacent to the right angle, so this side and this side, are called legs. So there are two legs and one hypotenuse in a right triangle. So we're going to use this right triangle and divide it up and use what we know about similar triangles and do a really cool proof of the Pythagorean theorem. So before we go on though, let's say, what does the Pythagorean theorem do for us? Well, it gives us a relationship between the legs and the hypotenuse. And it says that if we take each leg and square it and then add them together, so that's a squared plus b squared, that will equal the square of the hypotenuse. And so when we did problems with this before, we were missing one of these. We were either missing the hypotenuse or maybe we were missing one of the legs. But whichever one we were missing, if we knew the other two, we could use this relationship here, a squared plus b squared equals c squared, and solve for the missing length. Okay, so it's useful that way. But this is what we want to show. We want to show that if we square the legs, add them together, and then square the hypotenuse, that those two quantities will be equal. Okay, so let's look at how we might do that. Okay, so I have placed a line on this triangle so that it intersects this side, the hypotenuse at a right angle. So we have two right angles here. And so by doing that, I have now divided our original triangle ABC into two triangles. And with those two triangles and the original triangle, I actually have three triangles. So I'm going to name this point here, point D, is we're going to call the intersection of this line that I added here. So we now have three triangles, and it might not be immediately obvious, but they're similar. Look at triangle ADC. So I've got, let me point at these. So I've got this triangle here, ADC, and it has angle A and angle D in it. Now notice, right angle and angle A. Now notice that our big triangle also has a right angle and angle A. So that must mean that they're similar. So by the angle criterion that we talked about in lesson 10, triangle ADC is similar to triangle ACB. the big triangle. Okay? And so for the same reason, this other triangle, so that takes care of this small one here. Now we've got this medium-sized triangle here. It has a right angle, and it has angle B. Okay? Well, our original triangle has a right angle, and it has angle B as well. So by the same angle-angle criterion, I could say triangle BDC is similar to triangle ACB. Okay? So, because, let's see, where's my pointer? So, because BDC is similar to this big triangle, ACB or ABC, and ADC is similar to the big triangle, what that means is that these two have to be similar to each other as well. And that turns out to be true. They are all similar. They all have an angle A, an angle B, and a right triangle and a right angle. So with that established, we're going to move on to another diagram. In order to be able to talk about these triangles better, it helps to lay them out separately, because this triangle here isn't oriented the same way. So we're going to orient them the same way, and then we'll carry on. But we do know that these three triangles are all similar to one another. Okay. Okay, so now we have the three triangles sorted out. They had to be rotated, reflected, translated to be in the orientation so we can see the corresponding sides. So this makes it easier to look at them. Okay, so in the middle is our original triangle, and then on the sides are the smaller and larger ones that we divided out of it. So we're going to start with the two on the left here. And we can, because we know all three triangles are similar, we can write ratios of corresponding sides. And this is going to be done in a way that will lead us to what we're looking for, which is a squared plus b squared equals c squared. Okay, so it's kind of an elegant proof and fun to look at. And so what I'm going to start with here is some corresponding sides on these triangles. So the hypotenuse of the small triangle corresponds to the hypotenuse of the large triangle. And then I'm also going to write a ratio of the short legs of these two triangles. So that's going to lead to these ratios. Length AC, which is the hypotenuse of the small triangle, over length AB is equal to, so the ratio of the hypotenuses of these triangles is going to be equal to the ratio of the short legs. Okay, and the short legs would be AD and AC, length AC. Okay, so now that we have that proportion written, I'm going to substitute the lengths that we do know. We don't know all the lengths on these three triangles, but we do know A, B, and C. And so I'm going to rewrite this proportion, putting in those numbers. So length AC is B. Okay, length AB is C. Length AD we don't know, so we're just going to leave that at AD. And then we have a C again in the second ratio, which is also B. Okay, so when we have a proportion like this, or two ratios set equal to each other, what I know is that I can, if I multiply the cross products like this, they will be equal. So I can write that B times B, which is the same, well, I'll just write B times B. B times B is equal to C times the length AD. Okay, so that is B squared is equal to C times length AD. Okay, so that's going to be important. That's an important step right there. All right, so now we're going to look at, and let's just go ahead and switch to green. We're going to look at these two triangles here and write some more ratios of corresponding sides. And so this time I'm going to write the ratio of the long legs. So I've got length CB, which notice is also A. CB there corresponds to DB. So we'll write that over DB is equal to the ratio, and again we'll use the hypotenuse ratios. So here we've got AB, length AB, over length CB. Okay, so let's put in again what we know. Length CB is A, and it occurs twice, and then we've got AB that we know is C. So we've got A over length DB, which I don't know the value of. It's this length here, is equal to length AB, which is right up here, and we know that that is C, over CB, which is A again. Okay, so all I've done is substituted what I know. So AB right here is C, and CB is A, and here's CB again for A. Okay, so just substituted. So we're going to wind up with a similar relationship. We've got A times A is equal to C times length DB. So we get A squared is equal to C times length DB. Okay, now I'm running out of room, but I want to do one more step before we go to the next screen. So I have these two relationships. I have B squared is equal to C times AD, and A squared is equal to C times DB. But I want to know, I know for the Pythagorean theorem that I want A squared plus B squared. So I'm going to add these two together. So I could say that A squared plus B squared should be the same as, now I know A squared is this right here. So I'm just going to substitute that in. So A squared is C times the length DB. And B squared is equal to this right here. So I can substitute that in for B squared. C times length AD. Okay, so now I have this new relationship. So I've got A squared plus B squared on the left, and I've got some C's going on the right, but it doesn't quite look like C squared yet. So we need to straighten it out. Okay, so we're going to go back to our original triangle and rewrite this relationship and see what we can do with it. Okay, so we're back to our original triangle, and this relationship here, a squared plus b squared is equal to, and I added some parentheses just so we can see the terms here, c times the length db plus c times the length ad. Okay, so I'm going to start working on the right side of this equation. And I see that each of those have the c in it, so I can use the distributive property sort of backwards and call this c times something in parentheses. So it would be c times the length db plus the length ad. Okay, so normally we would use the distributive property, not normally, but you're probably more used to using it to take it from a step like this to that, where we say, since we have these parentheses here, we take c and multiply it by everything inside. So we'd have c times db plus c times ad. So that's exactly what we did. We just used it in a different direction. All right, so now what we need to do is think about what is this quantity right here. What is dB plus AD? And if you look back on this triangle that we started with, you can see that here is AD, here's length AD, and here is length DB. If you add those two together, you just get C. And so we have that this is C times C, which is of course equal to C squared. So we have A squared plus B squared on the left and C squared on the right. So we have shown, using similar triangles, that A squared plus B squared is equal to C squared for any right triangle. Okay, so that's a proof of the Pythagorean theorem. All right, so now we're going to look at just some problems using the Pythagorean theorem. Okay, so now we're going to move on to the classwork that you have in your notes. We're going to start with these exercises, and we're just going to be using the Pythagorean theorem to find unknown lengths in a right triangle. Okay, so in this first exercise, the length that is unknown is the hypotenuse. So we're going to use the relationship of a squared plus b squared is equal to c squared, and use that to solve for the missing length. And so down here I can see my two legs, 5 and 12, and the hypotenuse, which I don't know the length of. So I can write 5 squared plus 12 squared is equal to c squared. And I was asked, does it matter which one we call A and which one we call B? And if you think about it, it really doesn't, because this addition is commutative, so it could go either way. It doesn't matter which one comes first. So if you're unconvinced, you can try it both ways. Okay, so 5 squared is 25. I always have to do the exponent first before adding. And 12 squared is 144. Those two added together equal c squared. So 169 is equal to c squared. And so if you remember your perfect squares, that 13 times 13 is 169, then you see that c is equal to 13. So that's our missing side length there. C is equal to 13. It checks out to be longer than either of the legs, which we should be true, since the hypotenuse is the longest side in a right triangle. Okay, so look at part B now, and see what you notice about the two triangles. You might notice that the two side lengths we're given are proportional to each other. The corresponding side lengths are proportional. 0.5 times 10 is 5, and 1.2 times 10 is 12. And so we've got proportional side lengths, and the angle in between those two proportional side lengths are congruent. So I know that these two, because they're right angles, are congruent. These side lengths are proportional. Therefore, these two triangles are similar. So I could use that fact and go right to that C would equal 1.3, because it's going to have to be 1/10 of 13. But I could also check it out. 0.5 squared plus 1.2 squared would equal C squared in this case. 0.5 squared is 25 hundredths. 1.2 squared is 1.44. Just got to get the decimal point in the right place on these. So that equals C squared. So this would be 1.69 is equal to C squared. And if you check it out, 1.3 times 1.3 will equal 1.69. So that's our value for C. Okay. Okay, now try exercise 2 on your own. Pause the video and come back and we'll just quickly check your answers. Okay, here's the results for number 2. So in number 2, we notice that it's not the hypotenuse missing this time, it's one of the legs. So I can write the relationship b squared plus 4 squared is 5 squared. I could have switched these two terms around. It could have been 4 squared plus b squared equals 5 squared, but it won't change the outcome. So we've got b squared plus 16 equals 25. What I've done is subtracted 16 from both sides of this equation to get b squared equals 9. And you'll recognize 9 as 3 times 3, so b is equal to 3. And this is a famous triangle. This is the 3, 4, 5 triangle. It's the most famous right triangle that there is. Okay, so for this next one, it's the same issue. This is a dilation of this triangle here. So, but let's check it out. B squared plus 0.4 squared is 0.5 squared, or 5/10 squared. Simplifying it out, I get this. Here I'm going to subtract 0.16 from both sides to get b squared is 0.09. And doing a little checking, I can see that b equaling 3/10 or 0.3. I multiply it together, I get 9/100 or 0.9. So b is 0.3, which makes sense with my dilation idea here. Okay, so look at exercise 3 and see what you can do with it. We're asked to find the length of this segment here, QS. And we're given a hint to use the Pythagorean theorem twice. So work on that and then come back and pause the video, come back, and I'll show you a solution. Okay, let's go over this last exercise and then you'll be ready to go. So we were given the hint to use the Pythagorean theorem twice. So on this side, I've used this triangle here, and so I have 2 legs and a hypotenuse. This is also a right triangle or a right angle because I've got a straight line and that one is labeled over there. So I have QT, length QT squared, that's like my A squared, plus the other leg squared, 15 squared, is equal to 17 squared. So I can solve using this. I can solve for QT squared. So QT squared is 17 squared minus 15 squared. I took this term and subtracted it from both sides of the equation. So this gives me 289 minus 225, which when you subtract it out is 64. So this length, QT squared, is 64. So that means QT is 8. Okay, and by a similar plan with this triangle here, the second one, I get this st squared plus 15 squared is 25 squared. Solve it and take the square root, and I find that length st is 20. So I was asked to find QS, so all I need to do is add those together and I'll have my result. So length QS is equal to QT, which is 8, plus ST, which is 20. Oops, not 25, 20. So the length of QS is 28. And that is our answer there. Okay, so watch the video that I'm going to add to our playlist on the proof of the Pythagorean theorem using similar triangles. It's a really nicely graphically done silent proof of the Pythagorean theorem. And work on the exit ticket and problem set, and you should have no difficulty. It's fine if you want to use your calculator on these. All right, good luck.